Okay, so our next talk is from Professor Onur Mutlu. So let me give a brief introduction to Professor Onur Mutlu. Professor Onur Mutlu is a professor of computer science at the ETH Zurich. He is also a faculty member at Carnegie Mellon University, where he previously held the Stretcher Early Career Professorship. He has many research topics like computer architecture, computer systems, and hardware security, bioinformatics. He has also won a number of awards, including the Google Open Source Peer Bonus Award, Huawei Olympus Mons Award, Google Security and Privacy Research Award, and many other awards. He is also an ACM Fellow, IEEE Fellow, and also an elected member of the Academia of Europe. So today he will talk about the storage-centric computing. So let's welcome Professor Onur Mutlu for the talk.
Okay, thank you very much, Yu. It's a great pleasure to be here. Can you hear me well?
Yes.
Okay, great. And I wish I could be there in person, but I'm on travel and unfortunately I cannot be in two different places at the same time. I'm going to talk about some motivation for storage-centric computing, and then we'll go into a little bit detail on how to enable it. Hopefully it'll be interesting. If you look at systems today, computing systems are bottlenecked by data. And data is really key for many applications. Machine learning, genomics, all of these applications are data intensive. And they require rapid and efficient processing of large amounts of data, more data than we can really fit in our main memories today. So data is increasing, and we can generate more data than we can process. And we need to actually perform sophisticated analyses on data. And this is clear in machine learning. I will not go into a lot of detail since I have a lot to cover over here. But in machine learning, both computation and memory model requirements are growing exponentially. As a result, we need to actually have solutions that are scalable. And I believe storage is a great place to do this. And if you look at the other workloads like database workloads, graph analytics, data analytics, and data-centric workloads, they're all bound by data in the end. Some memory and storage access bottlenecks them. And if you look at the mobile end, on the mobile end, we're also bottlenecked by data. I will mention an area that we are working a lot on, genomics area. Here, data is really exploding. This is because we can design sequencing machines that can actually generate data at very low cost. And the cost of sequencing genomes is reducing much faster than the cost of a transistor is reducing today. And as a result, we're really bottlenecked by data again. And there are clearly many, many applications of genomics. I will not go into a lot of detail, but this is an area that we work a lot on. And this is actually a very good use case for customizing the storage system for an application like genomics, I think. Again, I will show you an example. This is a data generator today. This is a nanopore sequencing device. You can see that it's very small. It's also very cheap. It's also about $1,000 or so. And it's actually extremely good at sequencing any kind of genome. It was used for COVID-19 sequencing initially, and it's been used for many, many things. Unfortunately, this device doesn't come with any computation power or any kind of interesting storage. So you have to move the data somewhere else to do the processing. And as a result, it leads to a lot of overheads. Okay, so I think let me summarize the problem that I believe we're having today. We have very special purpose machines for data generation. This is another genomics machine. They're very fast. They're extremely good at what they're generating. Unfortunately, they're terrible data analyzers. To analyze the data, we have to move the data from those machines all the way to some other computers that are usually slow because they're general purpose. So we have two problems. One is we're doing general purpose computation on special purpose data. And the second is we're moving data all around, even though the special purpose machine actually has some storage inside it, at least the big one over here, as you can see. And this problem is actually relevant in not just genomics, but if you replace this genome sequencer with video cameras are all over the place, it actually sees the same problem. Or if you actually replace this with the way we use web today, people are actually doing clicks all over the place, and those are actually data that we generate. So there's a lot you can think about it. Sensors all over the place are also data generators. Okay, so I will not talk more about genomics, but the principles that I'm going to discuss today are actually especially interesting for genomics, but genomics is just a use case. So I'm going to skip these slides. I will tell you what we can do today. Today, actually, we're in a good situation. We actually have near memory processing capability using FPGAs, for example. And I will give you some results. And we also have interfaces like CXL that can enable in storage and in memory computing much better. But one of the, so for example, these are studies that we have done with IBM. We were able to accelerate important workloads like genomics and weather modeling inside this FPGA board, which is connected to high bandwidth memory at high bandwidth and low access latency. And we see significant speed ups, as you can see, to 27 times performance improvement and 1 to 2 orders of magnitude energy efficiency improvement. And this is great in some workloads. Unfortunately, this is good if your workload fits into memory. And HBM is great for near memory computing, but HBM is very low capacity, and many workloads actually don't fit. And the question is, of course, what do you do when the workloads don't fit? Okay, I'm going to skip some of these slides also. You can find a lot more information about genomics. I will get back to this from a storage perspective in a little bit. Okay. So this was an example. This was an example that shows that data overwhelms modern machines. It overwhelms our storage and memory capability, communication capability, and computation capability. And also data greatly impacts robustness, energy, performance, and cost. I'm not going to talk a lot about this aspect except for energy and performance, but robustness and cost are actually important as well. Now, if you go back to fundamentals, if you think about how we construct a computing system, we have 3 key components: computation, communication, and storage and memory capability. Over time, we have actually separated these components, and we actually placed a lot of importance on the computing unit, whereas communication and memory and storage units are kind of forgotten. Forgotten in the sense that they cannot do computation on data. As a result, everything has to move to the computing unit. And this actually leads to a lot of problems. So if you look at a processor today, and also accelerators, most of the system is dedicated to storage and moving resources that can store and move data: caches, interconnects, other caches, other interconnects, other caches, other interconnects, other caches inside the storage, other interconnects, and storage, of course, right? And if you do the calculation, more than 95% of the real estate of a single node is dedicated to structures that move and store data. Now, if you look at this picture, you would say, okay, we should really not be bound by data storage and movement. Unfortunately, the system is still bottlenecked by memory and storage today. And if you look at actually, if you don't like my picture, this is AMD's picture. This green box over here is L2 and L3 caches. And then there's the global memory interconnect, etc. Most of the chip is really dedicated to data storage and movement. And we're adding more by doing 3D stacking, which is an interesting technology, but it's not clear that adding more non-active components that cannot do computation on the data is a good thing for our overall system efficiency. That's true for IBM also, and I could keep going. This is another SoC. That's actually one of the more powerful SoCs that are out there today. And if you look at the system is mostly memory and storage, right? There's this darkness over here that's usually not depicted in many pictures, but it is there, and it's actually the thing that has enabled these systems. The SSD has enabled something like the iPhone to be successful significantly. If it was not there, then this iPhone would not have been as successful. But unfortunately, there's an efficiency problem because the processing is only done in the middle over here. Okay, let me give you some data right now in terms of this processor-centric design. We have analyzed a lot of workloads over many, many years. And this is some work that we did with Google. We analyzed these 4 workloads on a mobile system. And we found out that more than 60% of the total system energy is spent on data movement. This is assuming that your workloads actually fit in main memory. If you actually go to storage, this number increases much more significantly. Again, assuming that your workloads fit in main memory, more than 90% of the total system energy in some large neural network models are actually spent in memory. And again, if you go to storage, then the problem actually becomes much, much worse. Okay, so let me go into a little bit vision, and then I will describe some overview, and then we'll go into a little bit more detail. So I believe that we need to design intelligent architectures that can handle data well. So what does it mean to handle data well? We need to design our systems in a different way, meaning we should ensure that data doesn't overwhelm the components by rethinking the algorithms, architectures, and systems we design and co-designing these things together. I'm going to talk a lot about this. But also, I think we need to design our controllers and systems such that they learn from experience. So if you design a storage controller, for example, it should not be just based on heuristics, but it should be based on some learning that happens based on the workload characteristics, users' expectations, etc. And as a result, it learns over time just like a human. So if we have time, I will talk about machine learning-driven storage system designs. And I think this is going to be very interesting into the future. And also, today's systems, going forward, I think we need to explore, expose a lot more information about the data characteristics into the underlying memory and storage and processing systems, such that we can do better decision making. For example, data has lots of properties. It has locality properties, performance properties, it has privacy properties, security properties, approximability properties, error tolerance properties. You could keep going and going. None of these properties are conveyed in a methodical way to the underlying hardware, storage, and memory system, such that the storage and memory system can take better decisions in the system. For example, if you design a memory controller today, the memory controller makes decisions based on the characteristics of the chips, not the characteristics of the data that it's dealing with, because it doesn't know the characteristics of the data. It actually doesn't know the privacy characteristics of the data, for example, or error tolerance of the characteristics of the data. Going forward, I believe this needs to change. Okay, so that was kind of the vision. I believe today's computer systems are processor-centric. We need to move to a more data-centric paradigm. Today's computing systems make decisions that are dictated by human designers. We need to go to a more data-driven paradigm where system makes decisions by itself, and its decisions improve over time much better than what a human can do. And systems today make component-based myopic decisions as opposed to taking into account the characteristics of data. Going into the future, I think taking into account characteristics of the data is going to be a lot more important. And that's kind of the vision. I'm going to talk especially about the data-centric aspects of it. If time permits, I'm going to talk about data-driven a little bit, but I don't have time to talk about data aware, but it's also extremely important. And these are synergistic with each other. So to be able to do this, I do think we need to revisit the entire stack in the end or over time, because all of these actually cut across the stack. Okay, I'm going to skip that one. Now let me jump into data-centric, memory-centric, or storage-centric architectures. Even if you look at data-centric architectures, there are a lot of things over here that we need to do if actually data is the most important thing in the system. First, I think we should really not be moving data all around. We should be processing data where it makes sense, and I'm going to talk a lot about that. But I think we should also think about how to make our design decisions different in the system such that we can enable much lower latency access and much lower energy access to data. Today, I think there's a lot of overhead in our systems, both the software and the hardware stacks, that go against low latency and low energy. And I think we need to re-examine all of those design decisions going forward. Clearly, low cost is important, and intelligently managing data such that we can have robustness, security, and better cost and performance is important. But let's jump into the first one over here. I call this processing data where it makes sense. Basically, we should be doing processing anywhere, any component of computing, not just a processor chip or an accelerator chip. And if you look at the computing, there are many, many components over here, as you can see: DRAM, storage, sensors, interconnect, network interface controllers, etc. This is not a new idea. This idea has been developed in the 1960s. If you find older papers, please let me know. It's called processing in memory, but I'm generalizing it as processing, let's say, where it makes sense. Now, what's different today? I think today we have nowhere to escape, meaning that we're having a lot of problems with memory technology as well as storage technology. Technology scaling is not going as well as it used to go. As a result, we need actually a lot more intelligence in the memory and storage system such that we can overcome those scaling challenges. And also importantly, at the higher level, we're having a lot of problems with applications. Data access is a huge bottleneck. Energy and power are extremely important today. And today, data movement energy dominates computation energy. And also, our requirements have changed. We want performance, energy efficiency, and sustainability all at the same time. We're beyond the point where we say, oh, we want to gain performance, but we can expend a lot of energy to get that performance. That equation doesn't hold anymore. And I believe we can actually improve all metrics by minimizing data movement. Okay, so that's why I think in-memory computation is important. And also, if you look at this picture over here, a memory access consumes more than 2 orders of magnitude the energy of a complex addition. And in general, it doesn't make sense to actually move the data to the computation. It's a lot more interesting to look at moving computation to the data today. And this number is actually a lot larger in a storage system. So it depends on the technology you use for storage, of course, but it's more than 3 orders of magnitude. Okay, so basically, we're arguing for a paradigm shift to enable computation with minimal data movement. We would like to compute where it makes sense, where data resides, and we would like to make computing architectures more data-centric. And that's the idea of processing in memory and storage. There are many questions over here. We'd like to offload computation to the memory and storage device. Tell it, please do this query for us, and then it returns the result to the processor. This is still an accelerator model, but over time, it could be more distributed as well. There are many questions over here that I'm not going to talk about in detail. How do you design the software and hardware interfaces? How do you design the system software compilers and languages? And how do you rethink the algorithms and theoretical foundations of computing? So it's really an across-the-stack problem. If you think about computing, theory of computing has been very processor-centric. You count operations to determine algorithmic complexity. Going forward, I think algorithmic complexity also needs to be revisited from a data-centric perspective. Okay, so I will now give some examples, but before I do that, I will say that we're actually doing a lot of work on processing in memory and storage and caches, etc. I think these are actually very, very interesting all over the system. And if you're interested, there are a lot of resources that we put out, and you can find information online. I will mention one thing that's coming up. We have a real processing in memory storage, memory tutorial in Micro that's coming up this October. If people are interested in attending, this is completely online, and you can actually attend on YouTube or Zoom. Okay, now let's go into a little bit more detail on how to enable this. I believe you need to think differently from the past approaches if you want to enable processing in memory or storage. This is my taxonomy for processing in memory or processing in storage. There are two ways of doing computation, I think. One is using the operational properties of memory and storage structures, such that you exploit the properties of memory such that you do some logic computation. And any memory is capable of logical computation without actually adding logic to it. I'm going to talk about this in the second part of the talk. Processing near means processing near storage or near memory. You add logic close to memory structures. This is similar to what we do today, except you put the logic inside the flash chip, for example, or inside the SSD controller, etc. So technology can be many different technologies, clearly, and these will be coming. And the location is another thing that's important to consider. And there are many locations in the computing stack. I believe in the end, we should be doing computation in all of those locations, in all of those technologies, with multiple of these nature. So basically, a tuple of the three determines the processing in memory type. And one can actually combine multiple processing in memory types in a system. And this is why I think storage is very interesting, because the storage system already has multiple different memory types that all can be doing computation on the data. So let me give you an example of this taxonomy, processing using flash. The nature is you're exploiting the analog operational properties of flash. Technology is NAND flash. Location is storage, an SSD, for example. I'm going to talk about that. You can also do processing near storage. The nature is near storage. And then technology can be multiple things that are inside the storage device. So the overall vision is basically you have a heterogeneous computing device with hybrid memory technologies and storage. And you can actually enable data-centric design of systems and workloads. And this enables also application-driven customization. I'm going to talk about that in a little bit, but this is kind of the overall vision. You have these storage devices, let's say, interconnected with each other. Some of them are customized for genomics. Some of them are customized for machine learning. Some of them are customized for other types of machine learning. And some of them are customized for video, for example. This enables workload customized storage-centric computing. And this customization can be reconfigurable over time as well. Okay, I'm going to skip this because I already said all of these. But I think one thing I will mention over here is that we need unified interfaces for efficient and fast communication between these devices also. So interconnect is still extremely important in this sort of system. Now, let me give you some examples. I'm going to start with an easier example in the sense that we're going to talk about adding logic to the storage device or near the storage device such that we can do some specialized computation for genomics. This is work that we're doing. One of the works was published in ASPLOS in 2022. We called it GenStore, but we're actually doing a lot of other works that deal with a lot larger data sets today. Now, if you look at genome sequence analysis, first, after you sequence a genome, you need to map the sequences that you found to a reference genome. This is called read mapping. You align the reads to potential mapping location in the reference genome, and you could be doing this for many, many reference genomes. So data set size can grow significantly. So for each matching location, the alignment step finds a degree of similarity. So it's an approximate matching computation. And this is computationally expensive because you need to actually take into account sequencing errors and genetic variation, et cetera. I don't want to go into a lot of detail over here, but the way it's done today is basically you move all of the data to the computation unit, a CPU or accelerator. So there's a lot of computation overhead, but there's also a data movement overhead. Now, people have figured out ways of actually using heuristics in main memory, in the caches, and a lot of accelerators and filtering, such that computation overhead reduces, but the data movement overhead remains because you still need to move the data to main memory caches or the computation unit. In fact, data movement overhead grows from a fractional perspective because computation overhead reduces with these acceleration methods. So accelerators actually affected much worse than general purpose processors because accelerators reduce the computation overhead. So the key idea that we exploit over here is to filter the reads inside the storage system with small amount of computation, such that only those reads that need to be accelerated in the accelerator that require expensive alignment needs to be done in main memory caches and computation units. So this is basically the pictorial depiction of the idea. Basically, you move only little data when it's really needed for expensive computation. And there are also more details. Now the question becomes, what do you filter out? For example, exactly matching reads are easy to filter out because this is very easy computation to figure them out. And also non-matching reads are easy to figure out, a little bit more expensive, but they can be figured out. So I've given you the key idea. I don't want to go into a lot of detail, but you can actually design customized accelerators or FPGA-based accelerators near the flash controller over here. There are challenges, of course. You need to take into account different behavior across different workloads, and there are clearly limited hardware resources in the SSD. So initially, we don't want to modify the SSD significantly because that will hinder adoption. So we have different ways of reducing those hardware overhead. And again, I will not go, since we don't have a whole lot of time, I believe, I will not go into a lot of detail, but the paper has a lot of detail in terms of how to handle different types of reads from a genomic perspective. Okay, now let me give you some results. Basically, if you do this, you get significant speed up and energy reduction. The speed up ranges depending on what you can filter out and the different applications, but it goes up to 33x, for example, and the energy reduction goes up to 29x, as you can see. And we believe the potential is actually even larger because we were not able to test a lot of data sets over here, and the data sets that are especially large lead to significant reductions. And again, I've already, I think these are some examples over here that you can take a look at. I'm not going to the details over here. The bigger, I'm going to skip this one. I've already said those results, but if you're interested in the results, you can actually read the paper for more detail. And this comes at an area and power consumption that's relatively simple. You can see that it's very small compared to a high-end processor. It's also reasonably small compared to ARM processors that are really simple in an SSD controller. Okay, so this is one work. As I said, we're actually looking at metagenomics and different type of genomics applications today, which actually yield even larger benefits because the data sets are much larger. I will skip some of the other works because we don't have time, but I'm going to talk about the processing using storage approach, which is fundamentally different from processing near storage approach, because here we're going to exploit analog operational properties of the storage device as opposed to putting logic inside the storage device. And this can be applied to many technologies, but I think we need to revisit how to do this in huge technologies that we have today, like flash, as well as DRAM, and also SRAM, but also other technologies. I'm going to talk about this work, and this is the work. This is a work that enables in-flash multi-operand bulk bitwise operations with a single sensing operation and high reliability, and we get significant performance improvements clearly compared to a processor-centric design or in-storage processing, which is near storage, in other words, and the parabit work that was actually developed, which is a nice work that was developed the year prior. And we show that they're low cost and it requires no change to flash salaries. Let me give you the key idea. Well, I guess before I give you the key idea, why do we do this? Essentially, conventional systems have the storage bottleneck. I've already mentioned that. And if you do in-storage processing like I described earlier, this is nicer and this is better. But unfortunately, in the end, you're bottlenecked by the internal flash memory chip bandwidth. Now, if you really want to not be bottlenecked, you should really distribute the computation inside the flash chips. You can add in-storage units over there, but you can also exploit the analog operational properties internally. And that's what we're going to do over here. The goal is to fundamentally mitigate data movement by actually distributing the computation capability across the flash chips. And the idea, the high-level idea is we want to actually lay out the data such that we can do bitwise operations on it. So you have 32 different data pieces over here, they're pages. And you can actually do a bitwise AND computation by concurrently enabling and sensing those pages. So this is actually a 32 input AND operation on data, which is fascinating, I think. So this is the way it's enabled is using multi-word line sensing. And then, of course, reliability is always an issue. How do you actually make this reliable? We have a lot of real chip results over here that I will not go into detail, but you need to use single level cell mode, and you need to actually play tricks such that the programming is done carefully, such that you have you separate out different data encodings enough. Okay, let me give you the idea of a bitwise AND. So these are word lines or pages within the same block. If you actually concurrently enable two of those pages, what you get is a bitwise AND operation. Why? Because a bit line reads as 1 only when all of the target cells store 1 because of and they act like resistors. As a result, you get a 1. And if any of the target cells doesn't store a 1, it acts like a switch. As a result, you get a 0. So this is a bitwise AND operation. And if you actually, and you can actually generalize it to multiple word lines, not just 2. You can actually do it in 4. You can actually do it up to 48 word lines. So it's a 48 input AND in the end. You also, and the key here is you can actually do this via single sensing operation. You don't do sensing multiple times. You do sensing a single time. This increases latency a little bit, but that's also evaluated. You can actually look at the paper. I'm going to mention that briefly. Now, if you actually do the same thing, enable multiple word lines across different blocks, pages across different blocks, you get a bitwise OR operation because these are connected in a different way. They're not connected serially. They're actually connected such that they drive the same bit line. And the reason you get an OR operation is a bit line reads 0 only when all the target cells store 0. Otherwise, it reads as 1. Okay, so now bitwise AND and bitwise OR. This is beautiful. Then the question is, can you be functionally complete? Now, the good news in flash memory is that you already get NOT because of the inverse read operations. And then you can easily build NAND, NOR, XOR, XNOR. So any type of bitwise operation you can build. I will let you read the paper since we don't have a lot of time. We're actually working on how to enable this to be much more programmable based on some of the work that we've been doing on DRAM as well. Now, the question is, of course, how do you make this reliable? Making it reliable is not easy, in my opinion. If you actually do multi-level cell, we don't know how to make it reliable. So we actually go to single-level cell operation. Clearly, we're trading storage density for reliable computation, but it's better than nothing. And we can actually perform precise programming of the cell by trading some programming latency for reliable computation. And we actually tested this on many chips, as I will mention in a little bit. Okay, so we did the real device characterization with 3D triple-level cell NAND flash chips. And we use worst-case operation conditions. And we can see that this computation happens reliably in those cells, assuming we do the what we discussed. We also have a system-level evaluation for which I'll report some results. We have limited workloads, but we actually have a lot more workloads right now than what was published in the paper. So this is a summary of the real device characterization. Basically, we don't need any changes to the cell area of commodity NAND flash chips. We can have many operands. So for AND, we can have up to 48. For OR, we can have up to 4, with small increase in sensing latency, as I mentioned earlier. And our reliability mechanism significantly improve reliability of computation results. There's no observed bit error in the tested flash cells in the end. Let's take a look at these performance results a little bit. So performance results are good in general. So this is bitmap index, for example, or image segmentation, or k-click star listing. We have a lot more graph processing workloads right now. You see significant benefits on most of these workloads, especially those that are storage bound. And the larger the number of operands that they work on, the higher the performance and energy benefits, because as I showed you earlier, you can do 48 operand and bitwise AND operation at maximum. Okay, I can talk more about this, but since we don't have time, I'm going to refer you to the paper for the rest of it. Now, I should also mention that both of these paradigms, processing using storage and processing near storage, require some adoption challenges. And the question is, how do we enable adoption of processing in storage as well as memory? I think the challenges are actually very similar between memory and storage. We need to show applications and software. We need to ease programming. We need to come up with better interface and compiler and hardware support. We need to enable better system and security support, for example, that are important, because if the computation is distributed across processor, caches, memory, and storage, you need to actually have the support for these and communication interfaces for them. We need to design better runtime and compilation systems, I believe, and also infrastructure to assess benefits and feasibility. Maybe more importantly than any of these, I think we need to change our mindset. Because if you look at the way we approach computing today, our mindset is very processor-centric. People don't even think about sometimes doing computation anywhere else other than the processor or the accelerator, which is Ballneck by memory and storage. Okay, I've already mentioned this. So I think going forward, we need to build fundamentally energy-efficient, data-centric computing architectures. And also, this will enable us to become fundamentally high-performance computing architectures as well. And I think the key in the end is making sure that we minimize the data movement while doing computation in places where it makes sense. Okay, I think depending on how much time we have, I can cover this topic or I can go back to the conclusion. Any suggestions?
Thanks, Professor Mutlu. And because of limited time, so we can have only one question. So anyone?
Okay. Maybe let me conclude quickly. Is that okay? Okay, so I think just to summarize, I think we must design systems to be balanced, high performance, energy efficient. And this requires us to think about systems that data-centric, data-driven, data-aware. We need to enable computation capability inside and close to storage. And hopefully I've shown you that this can lead to orders of magnitude improvements, enable new applications and computing platforms. I strongly believe this actually, especially with the storage system, and maybe enable a better understanding of nature. So future is truly bright, but there's a lot of hard work to do in research as well as development across the computing stack. I will leave you with this picture because I think this picture is quite in contrast to how we do computing today. Computing done in this device is very different from, in my opinion, at least this device is built for computation in a very different way than we design our systems to do computation today. Okay, now we can take the question. Sorry.
Okay. A wonderful talk. Okay. Anyone? Okay, Professor Mutlu, I have a question. You mentioned there are two directions, like processing near storage and processing using storage. So what if combining them together, like potentials and challenges, or something like that? Oh, thanks.
Yeah, that's an excellent question. And I think, as I suggested, it should be combined together for the best benefit. I think the challenges would be, which one do you use for what workload or what part of the workload? So in the end, the scheduling and data management, data movement challenge will be internal to the storage system. But I strongly believe that it should be combined. And we actually have some initial results showing that combining these two types of processing in storage using and near are actually much better than either of them alone. Because, let me give you an intuition. With processing using storage, you can do bitwise operations extremely fast. But unfortunately, complex operations like, let's say, floating point computation is extremely difficult. So you need to partition your program such that you do complex operations near storage, but simple operations like logical operations that I mentioned using storage. And if you actually communicate as little as possible between those two, you can actually get much better performance and energy.
I see. Thank you. Thank you very much, Professor Mutlu. And okay, that's all. Thank you. Thanks.
Okay, thank you very much.
Good. Because of limited time, so we can only have one question. Thank you. Okay.
Thank you.
So, 我们下面一位讲者，好 ，Thank you.